Hello, class. This is Mr. Hart. In this podcast, I want to go over some of the things we talked about in chemical bonding week 3. And in particular, in this week, we started covering compounds and naming compounds. How we take a chemical formula and turn it into a actual name. Okay, so there's certain rules that we have to follow when we do this. Okay, so let's take a simple a simple compound like water, H2O. What would be the actual name for this compound? Well, we just need to follow some simple steps. So first of all, we just name the elements in that compound. Okay, so water is made of hydrogen and oxygen. Okay, so hydrogen and oxygen. Then we're going to change the last element in this compound to have an "ide" at the end. This is kind of a weird convention that they've made, but we always try to make the last element have an "ide" at the end. So instead of hydrogen oxygen, it's going to be hydrogen oxide. Okay, so notice that oxygen has changed, so that it ends with "ide." I don't know why they do this. It's just kind of a convention they've made. Okay, so hydrogen oxide. Then the last step is to determine the number of atoms for each element and write the prefix that goes with it. So, for example, if there's just one of that element, it's mono. If there's two, it's di. It's three, it's tri. If there's four, it's tetra. So we have two hydrogens, okay? So it's going to turn into dihydrogen. And we have one oxygen. So over here, we look, it's mono, so it's going to be monoxide, okay? So the full name for this compound is dihydrogen monoxide, okay? Simple enough. So we just follow these 3 steps and we can name basically any formula. But there's a couple of exceptions to these rules, a couple of things we need to know. So one of those is if we ever have a compound and the first element just has one, usually you would put the prefix mono, right, to designate one. But if that element is at the front, then we're just going to drop it from the name. Okay, so for example, CO2, okay, we have one carbon, one oxygen. You might think this is going to be called monocarbon dioxide, right? Monocarbon, one carbon, dioxide, two oxygens. But because of this convention, we don't care if there's just one in the front, okay? We just will drop that mono right out of there, okay? So instead of monocarbon, this just becomes just carbon, is how we say it, carbon dioxide. So you probably have heard of carbon dioxide. You probably never heard of monocarbon dioxide, okay? So that's one of the exceptions. We always drop the mono if it's at the front. Okay, then the second one is if the compound is an alkali metal with a halogen, okay, an ionic bond, then we don't state any prefixes. Okay, so for example, sodium and chlorine, okay, you might want to think this is monosodium, monochlorine, okay, but because it's an alkali metal, sodium's an alkali metal and chlorine's a halogen, we're going to drop both the monos. Okay, we're not going to state any prefixes. Okay, so this, instead of becoming sodium monochloride, this is just sodium chloride, which you've also probably heard. Okay, so these are the 2 exceptions. Always drop the mono at the front, and if it's a alkali metal with a halogen, or basically an ionic compound, then you don't state any prefixes. Okay, let's try one more example. Let's look at this one right here, SO2. So S, if you look at your periodic table, is sulfur. Okay. And O, as you probably know, is oxygen. Okay, but we know that we're going to state oxygen, since it's the last one, as oxide. Okay, we're going to change the N to ide. So this will be sulfur oxide. Okay, then the third step is to name the prefix. So there's one sulfur. So this would be monosulfur. Oh, and I just noticed I spelled sulfur wrong. That should be a U. Okay. So, but it's not going to be monosulfur, right? Because we don't state the prefix if it's at the beginning, right? We don't state the mono prefix at the so if it's at the beginning. So instead of monosulfur, okay, this is just sulfur. And then there's 2 oxygens, so that's sulfur dioxide. Okay. All right, let's do this one as well. Okay, so Xe is xenon. Okay, if you look at your periodic table, it's xenon. And F is fluorine. Okay, so we have fluorine, but instead of fluorine, we're going to change the N to ide. Okay, so this is going to be xenon fluoride. Okay. And then we look at how many we have of each. So we have one xenon, so this would be monoxenon, but again, it's at the front, so we're going to drop the mono. And then we have 4 fluoride, so this would be tetrafluoride. Okay, so the full compound name is xenon tetrafluoride. Okay. All right, and then if you're making a participation, go ahead and try these other 3 right here. See if you can figure out what we would call those. All right, let's move on. So not only can we name elements based on their formulas, but we can also find the formulas based on the names. So let's look at this one. So phosphorus, triiodide. Okay, so if we look at the periodic table, we know that phosphorus is represented by a P. Okay, and we know there's 1 of them because there's no prefix, which means it must have been a mono, right? That was dropped. So we have 1 phosphorus, and then tri, meaning 3, iodide. Well, iodide isn't an element, but iodine, with an N, right, is. And that got switched to iod, right? So this must be iodine. Okay? Iodine is represented with I, and we know that there's 3 of them because of that tri right there. So there you go. There's our formula. Pi3. That represents phosphorus triiodide. Okay? Let's try this one. So silicon is represented with Si. Okay, and again, there's no prefix, so it must have been a mono that was dropped, so there's just 1. And then tetrafluoride. Well, again, there's no chemical called tetrafluoride, but there is a chemical called fluorine. Okay, that must have been changed to ide, so this is fluorine. Okay, or F on the periodic table. And then there's a prefix tetra, so there must be 4 of them. Okay. Simple enough. So there's our chemical formula for silicon tetrafluoride. Okay, and if you're making this up for participation, go ahead and try and name these 2 down here, or find the chemical formula for these 2. Okay? All right, then we moved on to the different types of chemical bonds. Okay, you'll see in compounds. The first type is called an ionic bond. Okay, so an ionic bond is a special bond that forms when one atom is going to give an electron to another. Okay, so down here, here's an atom. It's going to give this extra electron away to this guy over here who needs just 1 more. Okay. Excuse me. Here's a better picture of this. So you probably have heard of sodium chloride or salt, right? Well, this is ionic bond. So think about sodium. If you look at its electron shells, it has this 1 valence electron sitting by itself. And sodium is going to say, hey, I just need to get rid of this guy, and then I'll have 8 electrons, 8 valence electrons. Because remember how every electron or every chemical's goal is to have 8 valence electrons or have that full outer shell? It wants to be like a noble gas, right? It wants to have a full outer shell. And so sodium says, hey, if I can get rid of this guy, then I'll be left with a nice full shell. Okay, and chlorine over here is saying, man, I just wish I had 1 more electron over here, and then I would have my full shell. So sodium and chlorine kind of make this deal. And sodium says, hey, I'll just give you this guy, okay, because I don't need him, and you really need him, so let's just make a switch here. So sodium gives away that electron, gives it to chlorine, and now they're both happy, right? Sodium has its full shell, chlorine has its full shell, and now they are bonded, okay, from this giving of the electrons. Because sodium is now positively charged, because it's missing an electron, and chlorine is now negatively charged, because it has an extra electron. And so the positive and negatives attract, and we have this bond. Okay, so this is an ionic bond where 1 atom is going to give that electron away to another atom, bonding them together. Okay? All right, and there's a little bit more vocabulary with ionic bonds. In every ionic bond, there's a cation, which is the positively charged atom or ion, or the one that gives the electron away. And then there's the anion, which is the negatively charged ion or atom, and that's the one that gets the electrons. So sodium in that example was the cation, and chlorine was the anion. Okay? All right, and if we look at the periodic table, okay, we can usually tell what types of groups are going to form ionic bonds. Okay. The alkali metals really like to form ionic bonds with the halogens. Okay. And the alkaline earth metals like to form ionic bonds with the halogens or column 6, sometimes even column 5. Okay. So, but the point is, these people on the very edge of the periodic table, column 1, column 2, and column 6 and column 7, they only need to get rid of or gain a few electrons. And so they really like to form ionic bonds. So if you see one of these guys with one of these guys, then it's probably an ionic bond. Okay? Then the next type of bond is a covalent bond. Okay? This forms when an atom, instead of giving its electrons away, it's going to share its electrons with another atom. So for example, down here, we have hydrogen and chlorine. Okay, hydrogen needs 1 electron, and chlorine needs 1 electron to have a full shell. So hydrogen just can't give its electron away because it only has 1. It still needs some electrons, but chlorine can't give any of its electrons away because it needs them too. So instead of one just giving it to the other, they're going to share electrons. Okay, so hydrogen is going to share 1 of its electrons with chlorine. Okay, and notice what happens. Hydrogen now has 2 electrons on its first shell, which is a full shell to hydrogen. Okay, so hydrogen's happy because it has a full shell, and chlorine's happy because it has 1, 2, 3, 4, 5, 6, 7, 8. It has 8 electrons on its shell, which is a full shell. So they both have a full shell because they're sharing this electron. Okay, so this is a covalent bond. Okay, anytime electrons are shared between atoms, that's a covalent bond. Okay, then we talked about this specific one. This is CH4, sometimes called methane, but it's also a covalent bond. Again, each one of these hydrogens has 1 electron, okay, which are shown with red dots, and the carbon has 4 valence electrons, right, which are represented by the blue dots. So carbon's going to say, hey, I'll share 1 electron with each one of you guys. So now everyone's happy, right? Hydrogen has 2 electrons. Okay, each one of these hydrogens has the 2 electrons it needs, and carbon now has the 1, 2, 3, 4, 5, 6, 7, 8 valence electrons that it needs. Okay, so now everyone has their full shell and everyone's happy. Okay, so this is why covalent bonds form. Again, the goal is always to get these full shells to make the compound stable. Okay, and again, if we look at the periodic table, the elements that mostly form covalent bonds are these guys over here, this box. Okay, really the kind of non-metals over here are more common to form covalent bonds. Okay, and especially these first 2 rows or so are especially common for forming covalent bonds. Okay, so if you see anything like with oxygen and nitrogen and carbon combined, that's going to be a covalent bond. Also, sometimes you'll see a lot of hydrogen bonding in there because it's officially a non-metal. So if you see hydrogen mixed with any of these, that's usually a covalent bond as well. Okay, or even like water, right? H2O, that's going to be a covalent bond. Okay. All right. Then we watched this video about ionic versus covalent bonds, which you can find here. And the last one is kind of a special one, which we call metallic bonds. Okay, these form, as you can guess, between metals. And metals are very special because they don't give or share electrons like the other compounds do or the other elements do. They actually kind of just let the electrons roam free, if you will. Okay, so instead of any atom worrying about specifically which electron's mine, all the atoms kind of form together and they let the electrons roam freely between them, which we call the sea of electrons. Okay, so electrons can move freely through the metal, and no specific atom is going to worry about which electron's mine as long as the electrons are there. Okay, and so this is why metals are such good conductors, because these electrons can just travel right through without any resistance, pretty much, because the atoms are willing to let the electrons pass by. Okay, and so there's a lot of unique properties we get from this as well. So good conductors, but also makes it so we can kind of bend the metals well, and they can absorb heat, And basically, just because they can move around a lot, we get these different properties. Because the atoms can move up and down, the electrons can move through freely, so it makes them unique. Okay, so specifically, some of the things that we can see is that it makes metals good conductors. Okay, because electrons can flow freely. It makes metals good heat absorbers because the atoms can vibrate without any resistance. It makes metals malleable or bendable because the atoms can move up and down, again, without worry about where the electrons are. And then it also makes metals so they have high boiling points. Okay. All right, so again, these are metallic bonds, kind of unique, kind of different from the covalent and ionic bonds. Okay. We also have a specific type of vocabulary word you want to look at, which is alloys, which is just a mixture of metals and other substances, which can sometimes give metals even better properties. Okay, you may have seen some of these, like brass is an alloy, stainless steel is an alloy, bronze. Okay, so you kind of just put the metals together, and again, because they're so willing to let things move freely through them, metals can combine really smoothly because they'll just let the atoms come in without any problems. Okay. Some alloy you probably have seen is steel, which is just iron and carbon. Okay, you just add those guys together, melt them together, and you get a metal that's stronger than iron and is less corrosive. Okay, and there's also stainless steel. There's a really good video at this link here that goes over how they make stainless steel very strong and less corrosive by adding chromium and these other substances. Okay. So in an overview, there's basically three bond types, and this is basically how we summarize them. So covalent bonds is the sharing of electrons, right, that happens between nonmetals. Okay, there's ionic bonds, which is when one atom gives an electron to another, which is between a metal and a nonmetal usually. Okay, and then there is metallic bonds, which just form between metals. Okay, and they are just letting these electrons kind of flow freely through the material. Okay, so there you go. That's a summary of what we've done. Also work on the compound worksheet if you have not already gotten a copy of that. Let me know if you have any questions about what we covered, and thank you for watching.